So we're back, and we were talking about power loss and power supplied, power, all that stuff. Energy is power is energy divided by time, so it's in watts. Okay, that's our unit. Can we eliminate power loss? And if so, how do we eliminate power loss? These inquiring minds want to know. Why would you want to know? Well, it makes everything a lot more efficient if you can push your current through and not have any loss, no heat thrown out of the system. That's fabulous, right? Everybody wants that. So, do you guys remember what allows us to do that? Is there a point if we take a certain material and we lower its temperature, to a temp less than some T critical temp. Sometimes, depending on the material, but sometimes the resistance, or let's say resistivity for that material, the resistivity goes to 0. Wow. If we can get our resistivity to go to 0 and we can make resistors out of it, then we have these resistors that if the temperature is less than some temperature, critical temperature, we don't have any loss. Power loss doesn't happen anymore. That is fabulous. Critical temp. That's this guy. Okay, that's our critical temperature for the material. No resistance. Wow. Now, to do this whole thing, well, okay, first of all, what do we call that? You guys have already said it in your head about 1,000 times probably. He's talking about this. Yes, you're right. I'm talking about superconductivity. So we've got our superconductivity. That's the name of the game right here. Now, to explain superconductivity properly requires one, quantum mechanics. So that's fine. There's a whole bunch of things we've got to determine quantum mechanically the density of. Why did I write G when I wanted a D? I don't know. Density of states. Oh, I know why I wrote G. Because the density of states is G. Okay. Well, all right. So we've got our density of states. Fine. I'm not totally losing my brain. Just mostly. Lower bound energy states. Look, there's things called Cooper pairs. And they're electrons. The whole thing, electron pairs. And they're far apart, and blah, blah, blah. It's a whole thing. There's this great big Bardem, Cooper, and BCS theory on superconductivity. You can look it up, Bardeen, Cooper, and I don't remember the third guy, but it doesn't matter. It's complicated, so we don't care about all of that theory. We just want to do what happens when we're in a superconductive state, okay? Or what is it? What can we glean from this? Well, we've got two types. There are two types of superconductors. Type 1 and type 2. Am I going to even talk about the differences between type 1 and type 2? I'm not even doing that. I don't want to. Yeah, let's not. We're going to just say there's two types. Yeah. If we've got zero resistivity, what are advantages that we can do for this? So let's talk about some advantages. So one, we can use in conditions of high current and low voltage, where normally we would have a lot of power loss, okay? But high current and low voltage, we can do this because we don't have any resistance. So this minimizes that power loss. Two, the detection of very small magnetic fields. So we can detect very small magnetic fields. Are very small magnetic fields, how small could they be? I don't know what the world record is, but 10 to the minus 14 Teslas, I don't know, maybe they've done 10 to the minus 15, but at any rate, that's small. Okay, so we've got small magnetic fields. What's something that would do that? Well, a squid. A squid is a superconducting. So let's do it. Superconducting quantum interface, quantum interference. Yeah, not interface. I didn't think interface was right. Interference device. Device. I don't know why I always want to put an I there. It's just one of those words for me. So device. That's a squid. Squids are used often with neurology, brain stuff, right? So we've got neurology. Another aspect when we're trying to detect these very small fields is nuclear magnetic resonance, aka, because nobody likes the word nuclear, it has nothing to do with decays of nuclear objects. It has to do with the spins of the nucleons, the nuclei. At any rate, nuclear magnetic resonance, aka MRIs. That's what we have now. Okay, so that's another. So we've got this, we've got this. Nuclear magnetic resonance isn't just for looking at people, by the way. It helps, and we can do it. Our computers allow us to calculate a lot of stuff from these spins of the. Here's our nucleus, right? I don't know, maybe it's carbon. It doesn't matter. It's got 6 protons in there, and it happens to be spinning with some omega, okay? And that spinning creates what? You guys know. It creates a electromagnetic field, okay? It's a current. So spinning gives us a current. Well, that's mu naught I, right? So that gives us a magnetic field. So yes, these very small magnetic fields can be detected and looked at, and that's what nuclear magnetic resonance is all about, okay? So it's a big deal. There's a lot of people into and studying nuclear magnetic resonances for many reasons, not just medical. So the third thing that can happen is what we call the Meissner effect. And the picture that I've drawn on my notes isn't a good one because, so I'm going to draw a new picture. I'm going to take some ferromagnetic material. Iron, okay? And we've got a cube of it. And below it, we've got this superconducting material. And the superconducting material is cold and whatever, all the stuff. But at any rate, this guy, let's change our colors here to magnetic fields. This supermagnetic, ferromagnetic, is wanting to produce, and normally would produce, I'll draw on the top, let's say the magnetic fields, okay, accordingly. The magnetic fields, oh, I'm doing a terrible job. This is not working out. Let's erase. That's not okay. Not okay. Ugh. Huge mistake there. Let's do the top. Magnetic field coming out of our guy, okay, and it wants to loop around. So it's coming out and it wants to loop around. Okay. However, it wants to loop around, and it can a little bit, but all of these guys, when they get here, they go like this. So a little bit loops around, but not all of it, because it can't. That's what happens in a superconducting material. It doesn't allow for magnetic fields to go through it. The magnetic fields go around it. So, therefore, You can look into the forces and all the stuff that are adding up here, but what happens is this thing has a center of mass, the mass times the gravity, but because those magnetic fields aren't able to come around and go where they need to, this thing levitates above our superconducting material, our SC material. Cold. Our cold SC material. So that guy will levitate. This is the Meissner effect. So really, what is the Meissner effect? The Meissner effect is the fact that the magnetic fields have to go around. Oh, I drew that with a... They have to go around this material. They cannot go through the material. It's a crazy... I don't know, an added phenomenon to superconductivity. So the Meissner effect. I don't like this drawing at all. There are way better pictures out there. You guys go look for the Meissner effect, and Google Images will have something sweet that'll show you a way better picture than that. A lot more descriptive probably too. So, okay, so nice. Let's get into why current flows. So we've got this electromotive force. The electromotive force. The electromotive force, we do EMF, or simply just E. And those are voltages. And what do we do? In a direct current sense, we have batteries. Or just straight up DC supplies. You can call it a power supply, or voltage supply. Okay. So what are we gonna say? Our voltage supply, or our power supply, these supplies are not perfect. They're not perfect. Since they're not perfect, what does that mean? Not being perfect in a sense, in a conductivity sense, means, what happened to the O? An electromagnetic force. It just means there's internal resistance, right? So we've got some battery, some Duracell, copper top, whatever battery. It's got terminals. It's got some current flowing out. This is the positive terminal. This is the negative terminal. It's got some current flowing in. What is happening on the inside? Well, let's look on the inside. Here's our imaginary line that is connecting on the inside. And we'll erase a little bit there, and we'll go like this. And we're going to erase a little bit down here. And we're going to go like this. This resistance is the imperfection of the battery. Okay? So resistance is internal. We call that RINT. All right? We've got an EMF for the battery. That's our electromotive force. And then the whole thing has a voltage for the battery. Okay? We call that battery voltage terminal, from one terminal to another. So that's terminal voltage or battery voltage. But we're going to call it V terminal for now because that's what the book does. And it turns out that if you do a little loop rule, you'll see that V terminal is equal to our EMF minus the current that we have flowing times the R internal. Let's get rid of some of these. What does that leave us with? The thing that we're looking for, the electromotive force, is equal to our V terminal plus that. So this is our EMF. Now, a lot of the times we've been using V and E, epsilon, interchangeably. And when we're doing that, we're considering the battery to be a perfect battery. If this is 0, if that guy is 0, then of course epsilon is equal to, our EMF is equal to our voltage at the terminals, right? So they're interchangeable. But technically, in the real world, none of these things are perfect, so we have to include an internal resistance. Yeah, I don't have much more to say about that, actually. So let's get into resistors in series and parallel. I'm not going to take a lot of time on this. I'm not going to derive anything. You guys have seen it. We've tested on it. So there's tests out there that you can study. There's the test reviews that you should study. I'm just going to state the equations. So let's do resistors in series. R equivalent. The nice thing is it's inverse. It's the actual opposite that capacitors do. So REQ for series is this. Okay? Now, if you were to do a capacitor, it would be 1 over the capacitance equivalent, and then 1 over capacitance 1, 1 over capacitance 2, right? But we do the opposite for resistors, and then in parallel, and I think learning capacitors are a better way to go. Learn capacitors first. And then do resistors. Resistors are easy. Capacitors are a little bit harder, but I think learning them this way isn't the way I learned it, and I appreciate it better this way. So parallel. Well, now we're going to do what we would do in series for capacitors instead of the other way around. And that's when we have N resistors in series and in parallel. Then you guys know the drill to figure out. I'm just going to draw some crazy resistors situation. We've got a resistor, we've got resistor, resistor, and we've got a resistor. So let's call this R1, R2, R3, R4. We eventually want to know what the equivalent resistance is for this, okay, for this whole circuit, okay? REQ, well, I would call that R1, 2, 3, 4, okay? And in order to get that, you got to kind of divide and conquer, right? We're going to take this bit right here and figure out what 2 and 3 are. Why? Because they're the only two that are in parallel with each other. And parallel is a little bit harder to figure out. It's more complicated. So we're going to do 1 over R2, 3 is equal to 1 over R2 plus 1 over R3. So we figure out what 1 over 2, 3 is. I'm not going to do it. It's a number. R2, 3 is equal to some number in ohms. Okay? So we've got R2, 3. Now we can do R1, 2, 3, 4, okay, which essentially is R1, 2, 3, 4 equals R1. These are all in series now, right? R2, 3 is in series. So R2, 3 is in series with R1 and R4. So that makes it easy, and that's our R equivalent for the circuit. So you want to do it that way when you get a chance to keep it simple. Just basically cut it all up into little pieces and parts and add the little pieces and parts in. Okay? So that is resistors in series and parallel. So let's go on. There's a couple of things about Kirchhoff's rules that I want to mention. Kirchhoff's rules. Let's just list them. Let's just list the rules first. So we've got 1, the junction rule. Okay, there's the junction rule. And what does that mean? That means we've got some junction. We've got current going in different ways. We're going to guess that our I1 is going this way, I2 is going that way, I3 is going that way. Okay, that's just our guess. But one of the things that you have to do is you have to say, well, everything going into this point A, everything going in, what's going in? I1, equals everything going out, I2 plus I3. Now, conservation of charge is where this stems from, because all the charge flowing in has to equal all the charge flowing out. So this is conservation of charge. Technically, between me and you, conservation of charge is conservation of energy, but nope. Conservation of charge. That's where we're at. And 2, the junction rule is the first one. The second one, you guys already know, because you know what? I think you guys like the loop rule. The loop rule, that one's better, right? Everybody loves the loop rule. What do we do in the loop rule situation? Let's just use resistors. Should we just use resistors? Yeah, we're going to see it again later with a capacitor in there. So let's just use resistors. I'm not going to put a bunch of voltages in there. I'm going to put one. We've got one EMF. And we have to have a junction or it's no fun. Okay. Yeah, good. So what are we going to do? Let's label R1 here. We'll label this guy R2, R3, and R4. We'll put a point here and a point here. We can label those if we want. We can put that, make that A and B. Let's look at the junction rules for this first. We've got current I1 going across R1, okay? We've got current I2 going across R2, and we've got current I3 going across R3. Nice. We're going to look at junction rule for point A. Everything going into point A is I1. Everything coming out of point A is I2 and I3. So that for our circuit is our junction rule. Now we can do the same thing. This is point A. We can do the same thing for point B. What good is it? It's going to give us the same equation. I2 plus I3 equals I1. So that is a redundant equation, and we don't care. We're not going to do it. I'm not even going to write it down. It's redundant, so we don't care, and we can move on. Now, what about R4? What's the current across R4? Well, it's in series with R1 and the battery. So since it's in series, I1 has to be the same, right? So R4 is going to have I1, and the battery itself is going to have I1. Okay? So if it has internal resistance, which we're not counting, but if it did, we'd have to include that, okay? So, all right, maybe R4 is our internal resistance for the battery. Yeah, I mean, that's a good notion right there. Okay, so let's do our loop rule. We're going to do 2 loops. Here's one loop. You can draw your loops any way you want, one direction or the other. It does not matter, okay? So we're drawing our loops. How do we do this circuit analysis? Okay, so the circuit initially, all it shows is an EMF, an R1, R2, R3, and R4. It doesn't show anything, currents. We've labeled A and B points. It doesn't show any of that. It doesn't show our loops. So what is the first thing that you want to do? You want to draw your best guesses for the currents. Okay, so draw best guesses. Why do you want to draw the best guess? If you're pretty sure that the current across R1 is going to flow in the I1 direction the way I've got it, then you want to do that, right? Because if you have it flipped around, then you'll end up in the end with a negative I1, which means you wrote your I direction backwards. Okay, so you want to draw it in the right way so you end up with a positive, and then you don't have to switch everything around. But it doesn't matter. If you end up with an I that's going in the wrong direction, that's okay. You just say, well, it's going in the other direction. Okay, so draw your best guess for the current's direction. Okay, B. Draw your loops in the direction that you want. Okay, now, there's a third loop on the outside. That's loop 3. Okay. So those are my 3 loops. I like going clockwise. It doesn't matter. The main reason I'm doing loop 1 clockwise is because it's going to give me a positive EMF, and I like that. Don't ask me why, I just do. Simple. So, and then since 1 is going in a clockwise, I did 2 clockwise and 3 clockwise. So the loop direction doesn't really matter as long as you pay attention to the rules, okay? So draw your loops. And it's important that you know which direction your loop is going. So have an arrow on the loops with arrows. Okay. I drew 3 loops. So now here we go. We're going to start developing our equations. So we have to take start forming equations. That's our part C, right? Well, that's a little trickier than you might think. Start forming equations. Pick a spot, okay? You can pick any spot you want. Let's use A. Okay, let's use A as our spot to start. So we're going to go around loop 1. We're going to start here. We're going to go that direction, and then we're going to come back to A in the end. Okay, so that's the first thing. So pick a point to start and end. Two, you got to start asking yourself a couple of things. So if the loop arrow and current arrow are in line, pointing the same direction, right? Then it is a voltage drop. You have a voltage drop. Okay, across a resistor. That's important. Or a component or whatever, but across a resistor in particular. All right, so let's do across the resistor. So let's do period. We're going to roll up just a little bit. And I kind of want to delete that thing there. Okay. So R2 will be our first one. Our loop is going in that direction, the same direction as the I2, and so they are in line with each other. So I have a voltage drop. So if I have a voltage drop, I'm going to say I2 R2 with this negative sign out front. Okay. You keep going. You keep on going with these things. If the loop direction and the current are opposed, if they're anti-parallel, opposed, then it's a voltage increase. Or gain. So it's a voltage gain. Do we have a voltage drop across R4? No, we don't. So I and our loop are in the same direction. So I1, R4. Now what happens when we get to our battery? Okay, we get to our battery and we're going from the negative to the positive. And so negative to the positive is going to give us a voltage increase. So the voltage there is E, epsilon. So that's great. And then lastly, we're going to have another voltage drop, I1 and R1. What does all that equal to? 0. Okay, all of that equals 0. That's one equation. So we've got a couple equations. We've got equation 1 here. We've got equation 2 here. Let's just write down, I want to write down minus to plus on EMF is positive, plus to minus is negative. Okay, so those are our rules. And now let's do loop 2. So loop 2, we've got I3, R3. We're starting at A again. So we're going to go in our loop direction. The first thing that happens is I3, R3. They're both in line with our loop. So we've got minus I3, R3. And we've got I2 going down, but our loop is going up. So we have to add I2, R2. And that equals 0, and that's our third equation. Our third loop, let's do our third loop. We're going to start at A. We're going to go down. The first thing we come across is that resistor 3, I3, R3. Same direction as our loop. We get to R4, same direction. The current and the loop are going in the same direction, I1, R4. We get our EMF. We have to add because it's going negative to positive on our EMF. So we come in here and we say, okay, we're going to add our EMF. Then we get to R1, R1, I1. All of that is going in the same direction as our loop. So I1, R1, and all that equals, let's say over here equals 0, and then that way I can draw my fourth equation. Okay, so we have all of those four equations. Four equations that tells us we can have four unknowns. Okay, how many objects do we have? How many things out there do we have? Well, let's list them. We've got four currents. Four currents? Three currents. So we've got I1, I2, I3. Those are our three currents. We've got a few resistors. How many do we have? We have four. So we've got R1, R2, R3, and R4. Lastly, we've got our EMF. Okay, so that's how many things are there? We've got one thing, two things, three things, four things, 8 things. 8 components, or I shouldn't say components. 8 things that are in question. Okay, we don't know those 8 things. So if we have 8 things that are out there, but we have 4 equations to solve, and we can solve for all of the unknowns, then 4 of those things have to be given to you. 4 must be given. So a problem like this, all I have to do is give you 4 of those things, and then I know that you can solve for the rest. Depending on which 4 I give you, I can give you 4 of them, and it doesn't matter. And some of the combinations will be more difficult than the others, right? Especially if I don't give you currents and the EMF. If I just give you resistors, it's doable. Do I have to give you one of the currents at least? I'd probably give you one of the currents and then maybe leave off the EMF and one of the resistors. But at any rate, yeah, 4 must be given, and then you can solve. So what's next? Okay. Measuring voltages. We want to measure voltages. We want to measure currents. We want to measure resistances. So we can do all of those things. How do we do it? Well, this isn't the old days. This isn't olden days. We have multimeters. Or we have lab equipment that we connect properly, and it will give us things. So let's do number 1 here. We want to measure voltage. Let's say we have a resistor in a circuit, and we want to measure the voltage drop or gain across that resistor. What are you going to do? Well, you're measuring across, so that tells you a little something. You're going to want A and B, okay, VAB. So you want VAB, you have to take your voltmeter and attach one lead to A and one lead to B, and it will either give you a positive or a negative, but it'll be the voltage across A and B. Okay, so that's voltage. You have to do it across the component or across the circuit or across whatever. But you have to have 2 points in the circuit that you connect to. 2, we're going to measure current. So we've got a circuit. Let's put a little break in there. And we'll put a resistor over here, and we've got it coming back. So we've got our EMF here. All right, so we want to know the current. There's going to be current through here. What is that current? How do we measure that current? Well, we put in place, in series, our ammeter. Okay, so this is a voltmeter. This would be an ammeter. And it's in series, so we have inserted it into 1 point. We're not taking 2 points. We're cutting the wire, putting our ammeter in, and then continuing on. So the ammeter is not connected across 2 things. It is inserted in series. In series with the wire that we want current through. We want resistance now. We want to measure the resistance. Of course, you have to switch your voltmeter, your multimeter. You got to switch from voltages to currents. And you got to do it right? You got to select the right scale and everything. Otherwise, I've been known to, you might in the future fry your multimeter because you don't have the right selection. Digital multimeters will fry easier than the old galvanometers, which is what I still use actually because I tend to fry multimeters. You want to measure the resistance. You do the same thing as you would in a voltmeter, but here's what happens. You've got your meter here. You've got it set for resistance. And what it happens is it sticks out, it puts out a known voltage. And a known current. I almost wrote voltage again. A known current. Well, it's putting those things out, known voltage, known current, through a certain resistor, then you're going to get whatever that resistance is. Okay, and ohmmeters are pretty good if you can just take the resistor out of the circuit. Now you don't want you don't want it to be in the circuit. You don't want other things happening, right? You want to have you want to remove that resistor from the circuit, because if other currents are flowing in and you're sending in your test current, then things kind of get a little bit muddled. You'll still get a pretty good, because of the junction rule and all that other stuff, you'll still get a pretty good, because this will still be the current going away. So all you've done is added some current and subtracted some current out. You'll pretty much get a good, but don't mess around. Take it out of the circuit, measure your resistance, put it back in. So that's how the digital multimeter will measure your resistance. So I'm just going to scrub 3, put 3 over here. Okay, that's how it works. V equals IR, and you're done with that. Well, another hour has come and gone, so we're going to get to whoa baby, we're going to get to RC circuits next, and we'll continue on our journey to the final. Not to the final 4. This is just our journey to the final. All right. Let's kill this.